Hello everyone, this is part 2 of the day 1 circuitry physics 11 note, and we are going to continue now with power. Go Power Ranger. I'm sorry, this is like way earlier than your time, but that was like one of the animated that was so on TV every day when I go home when I was in high school. So Power Ranger, go for it. Yay. Now, has nothing to do with what we're talking about in here. So I need to recall that power from our previous chapter, our last chapter on energy and power. Power is the rate, right? It's the rate of doing work. Power is the rate of energy consumption or energy transfer. So remember that power, remember the equation. Power is the amount of energy that an object consumes or use every second, right? So hopefully you remember that. And the unit, so another reminder, right, is the unit. So if you have power, is measured in watts, right? W-A-T-T, watt. Okay. Now, but we have to look at something else though. Now I'm going to do a derivation, which won't be very long. So remember, current is the amount of charge passing by a point every second. And voltage is the amount of energy carried by 1 coulombs of charge. Now, what happens if you actually take the current and multiply by the voltage? If you take the current and multiply by voltage, what you discover is something like this. So current is Q over T. Voltage is E over Q. Wait a second, then the Q cancels out, and we are left with an equation that has energy on top and time on the. Wait. That is strangely familiar. We just wrote that. That's power. Oh, so if that's the same, does that mean these two are the same? Yes, it does. Okay? Yes, it does. So we have just derived an equation for power specifically for the circuitry unit. Okay? So power is also defined as in a circuit by current times voltage. So if you know the current, if you know how many people are delivering the pizza to you, and you also know how many pizza they each carry, then you'll be able to find out your power, which is the amount of pizza you consume every second. Technically, that's how my definition works in here too. So power, which is the amount of energy the object, for example, your cell phone, consumes per second, or is equal to the amount of current going in multiplied by the voltage drop when the electron makes their delivery of energy. Okay, it makes perfect sense. So it's the amount of electron going through you multiplied by, well, how many pizza do they carry? How much energy do they carry each? So that total number will give you the amount of energy consumed, the amount of pizza consumed by the device in every second. But we also have Ohm's law, right? So Ohm's law, which is the famous V equal IR, right? So what happens if you take Ohm's law and you replace the V with Ohm's law? Well, then this equation, power, become I times R. Well, then there's 2I then. Yep. So 2I multiplied by together is called I squared. So I square R. Oh, so in order to find out, so to calculate the power rating of a machine or device, you can do it with this method, which is the current times the voltage across that device. Or you can also do it this way if you don't have the voltage. If you know the resistance of the device and you know the current, which is the amount of electron going through you per second, then you can also measure your power rating this way. You can measure how many joules of energy are you using per second this way. There's a third way of doing this, which is solving Ohm's law for current. So I is equal to V over R. So solving Ohm's law for current, and then substituting that into the power equation once again, but this time substitute that into the current instead of into the voltage. Then you get a third equation. Okay, so then you get a third equation. So that case, you get something like this. You get power is equal to, so I is gone, right? I is replaced by V over R. And then, so V over R. And then you have another V. So V times V is, well, so that leads to power equals to V squared over R. Okay, so that is the third format of the power. So these three equations are all very useful. I think the formula sheet only has one of them, or maybe it has all three. I will have to double check. But here we go. So power in a circuit. So the power of a device. So how much energy does that device use per second? Remember, that's what power really is. The power of a device is either obtained by voltage times current, or if you don't have voltage, current squared times resistance, or if you don't have current, voltage squared divided by resistance. So you can find power this many ways. Okay, so depends on what you have. So if you have current and voltage, you use this one. If you have current and resistance, you use this one. If you have voltage and resistance, you use that one. I'll just do a couple of examples really quick for the first one. And the second one, quite easy. And the third one will look actually a bit hard. Okay, so an electrical fan has a resistance of 12 ohms. So that's resistance, 12 ohm. And it requires 0.75 amp. So current is 0.75 amp. To run, what is the voltage required? Now, this is a very, very straightforward Ohm's law application, because Ohm's law is V equal IR, right? V equal IR. We have two out of the three things, so it cannot get easier than that. So we have voltage is equal to I, which is 0.75, multiplied by R, which is 12 ohms. So that will get you 9 volts. So the battery is a 9-volt battery. Okay, so that's one. Super quick, right? Okay, so let's look at another one. The third one is a scary one. So this one is not. Okay, so we have a electrical heater with a 100 watt. Now this is the power rating. So the power rating is 100 watts. When connected to a voltage, that's 120 volts. So voltage is 120 volts. What is the resistance? So I'm looking for R. Now, whenever you have power in your equation given, or you're looking for power, you need to use one of those power equations. But what do you have this time is I want voltage and resistance, right? We want voltage and resistance in the equation. So this one, voltage and resistance, that one is the best. The other two, you cannot use them because you don't have current. If you don't have current, you can't use the other two. So use the one that you have a rating for. So power, so we're going to use the V squared over R equation. So we have the power, which is 100 watts, and we have the voltage, which is 120 volt, but we don't forget to square it. It's actually 120 square, and then we're looking for resistance, which is right here. So how do you do this? So algebra, right? So switch to 2. So you have your R up here, and it's 120 squared over 100. Okay, and that you just take a calculator, 120 squares, and then divide by 100. So this will turn out to be 144. Now resistance is measured in ohms. So 144 ohms. There we go. 144 ohms. Still easy. Still easy. Okay, so the next example is actually going to be a little bit hard. Okay, so this one, example, when a 12-volt car battery, now, so in your car, the battery is a 12-volt battery. It powers any electronic devices that's actually in your car. And a single 30-watt headlight. So your car has headlight. Now, let's say the battery is 12 volt and the headlight is 30 watt. That means it needs to consume 30 joules of energy per second in order to actually light up. How many electrons do you need to actually go through the headlight for you in 1 minute in order to power it? Okay, so what is the question actually asking? Is how many electrons passing through the headlights every minute in order to actually turn it on. Now, why do we need the electron passing through it? Because the battery is not going to magically make the light bulb light up. The battery needs to collect to the light bulb, and there needs to be electron bringing the energy from the battery to the light bulb. So how many electrons are actually going through the light bulb in 1 minute? Okay, now that is related to current. So we're going to find current first. Now, unfortunately, current is measured in every second. So this is 1 minute. So we will have to do some change later on. Okay, now let's start by having power. So power, if I want current, I have voltage, then I'll use power equal IV. That's one of the power equation. So my power is 30 watts. My voltage is 12 volts. And my current can be found this way. So 30 divided by 12. So my current is going to be 2.5 amp. Okay, so 2.5 amps. So that's the power. That's the current. So what does that mean? This means 2.5 coulomb of electrons per second. Okay, 2.5 coulombs of electron per second. Now, that doesn't tell you how many electrons though. You see how this question is actually kind of weird? That doesn't tell you how many electrons. You know there are 2.5 coulombs of electron going through the circuit every second, but you don't know how many electrons. Okay, so what do we do? What do we do now? Okay, so now this is per second, right? So at least let me find it for per minute. So the question said in 1 minute. 1 minute, right? So then in 1 minute, how many electrons pass through? So instead of 1 second, 1 minute. Now that's easy. Just take that number, multiply by 60, right? Because the definition for current is charge per unit time. So if your current is 2.5 amp, 2.5 amp, and the time is 60 seconds, 1 minute is 60 seconds, then the amount of charge, right? The amount of charge has to be 100, so 2.5 times 60, 150 coulombs. So 150 coulombs of electron in 1 minute. So in 1 minute. Okay, so you say, Mr. Chang, are we done? 150 electrons. No, 150 coulombs of electron is not the same as 150 electrons. Remember, it's like 1 kilogram of sugar has a lot of little tiny grains of sugar in it. Okay, so what do we do next? Now we have to change that. Okay, so think about it. So the charge of 1 electron, so a single electron, if you only have one, right? The charge of 1 electron is what? Is the elementary charge value. 1.6 times 10 to the negative 19. Now, you might say, Mr. Chang, isn't that negative? Yeah, but we are just counting numbers of electrons in here. It's not like we'd have a negative sign in our charge. So how many electron each carrying this, well, each is 1.6 times 10 to the negative 19 coulomb, do you actually need to make up 150 coulomb? Okay, so the number of electron. So number of electrons is going to be, okay, so you have 150 coulomb divided by every electron has 1.6 times 10 to the negative 19 coulomb. So how many electrons will actually make up 150 coulomb? So the answer turns out to be, so the number of electron turns out to be 9.375 times 10 to the 20. So how big is that number? Okay, how big is that number? That number is, I think, 900 billion billion? Yeah, 900 billion electrons. So that means for every minute that you're actually using your headlights in your car, there are 900 billion electrons carrying energy from the battery to the headlights and deposit it to the headlights and go back to the battery and doing it again. Every minute, 900 billions of electrons are actually working for you. That's a crazy number. Now you will see questions from the homework that are actually similar to this type. So that's why I have these examples in here. Now, the rest of this is very quick. So direction of current. So which way does the current flow? It's actually weird. So now, okay. A battery. Oh, you know what? Before we do that, because we will need to use schematics, can we actually skip to the next page so that I can draw the schematic diagram for circuit symbols? So when you draw circuit, you don't actually draw those battery by drawing the battery because that would take too long. Okay, so we have a special way of drawing things. So a cell is usually represented by this, a short line. These are the two terminals of the battery. The shorter line end is the negative terminal and the longer end is the positive terminal. And that's a cell. So this is a cell and this is a battery. How many people actually remember what's the difference between a cell and a battery? A cell is one. When you have more than one, it's a battery. You can have like 3 battery, but one cell. Okay, so when you buy a battery, if you only bought one, you have a cell. But if you bought like 16 of them, then you have a battery. Okay, if you put like 16 batteries together, 16 cells together, it's called a battery. It's just pearl, right? Wire. Wire is just a line. That's easy. Junction. Sometimes you have wire that splits up. It's called junction. Okay, so the point where the wire split up is called junction point. Junction. Resistor. Resistor is anything that is consuming energy a lot of times. So resistor is represented by something like this. Okay, now, so why do we put resistor in the circuit? To waste energy. Because sometimes you have a battery which come in standard size, but your machine doesn't need that much energy, so you can't fit all the energy into the machine. So you need a resistor to waste some of the energy so that the rest of the electronic doesn't actually blow up. Okay, so this is a light bulb. So a light bulb is another thing that we draw on a circuit diagram a lot. So a light bulb, like that. Okay, a switch can be open or closed. It's an on and off button. So that's an open switch. That means the electron cannot go through. And this is a closed switch. That means the electron can go through. So the pathway is complete. So closed circuit. Now we have 2 devices, which we'll talk about in a little bit, but that's good enough for now. Let's go back to the picture here. So we're going to draw a cell, one cell, right? And then we're going to have so we're going to draw a cell in here. And then we're going to have it connected to, so like right here like that, like this. And we're going to have it connected to a resistor. Like that, and come back. Now, okay, so remember this is the negative sign and this is the positive sign. Okay, so now, if you remember, electrons are negative, right? So therefore, electron is repelled by this side. So electron want to go this way. And that's exactly what electron will do. Okay, so electron is repelled by the negative terminal and is attracted to the positive terminal. So electron actually float like this. Okay, so away from the negative and going into the positive. Okay, so this is the direction of the electron flow. Okay, so the direction of the electron flow is from the negative terminal to the positive terminal. Okay, from negative to positive, the direction of electron flow. Okay, now it would be very nice if that's the direction of the current. Unfortunately, the direction of the current is this way. Okay, is from positive to negative. This is the direction of the current. Okay, so that's the direction of the current. Okay, now some people might ask, okay, Mr. Chang, this is not making sense. What is actually going in the current direction? Nothing. So in the circuit, electrons are going in the green direction from negative to positive terminal, delivering energy, just like what we said. But there is actually a story, kind of sad, about how scientists make a mistake long time ago. We thought electrons were positive for the longest time. Okay, so that's it. Like the basic one sentence version of the reason why our currents is in the wrong direction compared to the direction that the electrons are actually going is because we thought electrons were positive before we actually discovered electron. So long time ago, scientists realized that in order to deliver energy, you must have something carrying it. We thought the object that carries it is positively charged. And now that was an honest mistake because we just randomly put a charge in there, right? That's before we actually had the technology to detect electrons. And then later on, we actually were able to detect electron. Now, the person who helped with that study, so in 1752, a person called Ben Franklin, which, hey, is actually on the US $100 bill, chooses a convention. So they just choose one way. They thought that electron were a positive charge carrying the energy. So we developed all our equation and theories assuming that the electron were going in the current's direction. Now that's in the 1700s, right? So what happened is a few hundred years later, we actually has the machine and technology to detect electron, and then we check it. So in metals, the charge carrier that's actually carrying stuff forward is the electrons. And we detect the electron, and guess what? It's actually negatively charged. But by definition though, by this time, all the theories about circuitry has already been developed. That means there are a lot of textbooks, a lot of people who assume that the electron was going the other way. So now we are down with two options. Either change all the textbook in the past like 500-600 years so that it reflects the directions of the actual electron flow, or just ignore it and keep the wrong way. And guess what? We picked the latter. We decide to actually just keep the currents in the wrong direction, and because it doesn't actually affect any calculation, whichever way it goes, it doesn't affect the calculations at all. So right now, when people ask you which way does the electron flow, from negative to positive, because electron gets repelled by the negative side, but which way does current flow is from positive to negative. Okay, currents flow from the positive to negative. Now, in this class and in every single textbook that you will see in physics or in engineering especially, right? A lot of you want to be an engineer. We will always use conventional current when we say current. So we will always use the other direction. Convention means tradition, right? So traditionally, that's how we call it. So that's why it's still going that way. So it was a mistake that was made like a few hundred years ago, but we are sticking with it because it's convenient. Okay, so final two objects. Okay, now, so we have all the schematics. So how do we measure voltage and how do we measure current? We have a little machine to actually measure them. When I go back to school, I will take a picture of it so that I can show you. It's called voltmeter and ammeter. So if you want to measure voltage, you use a voltmeter. The symbol for a voltmeter is a little circle with a V. That's it. And then you collect it to something, right? And ammeter is a little circle with an A. So voltmeter and ammeter. Ammeter measures current, okay? Am, right? Ammeter measures current. Voltmeter measures voltage. So this measure current. Measures current, okay? And this one measure voltage. The voltmeter measure voltage. Now, but there are certain rules that you need to know. They had to be collected slightly differently. You can measure voltage in a circuit using a voltmeter. Okay, and you can measure the current in a circuit using an ammeter. But you need to collect them differently. Now, voltmeter must, okay, so it's not an option, must be collected in parallel with the item that you're actually measuring. Okay, so voltmeter must be collected in parallel with the object that you're trying to get the voltage on. Now, parallel means you hook it up like this. Okay, so parallel means you hook it up like this. So for example, let's say you have a battery, a cell, and you have a light bulb, and you would like to know how much pizza is delivered to this light bulb. Maybe you have more than one, so you don't know how much go to the first one and how much go to the second one. Okay, so let's say you want to measure the current across the light bulb. We use the voltage, sorry. You want to measure the voltage drop across a light bulb. Now, we call that a voltage drop because usually the voltage will drop if the energy will drop, right? The amount of pizza will drop if you go through something that uses energy. So let's say this light bulb is actually lighting up, then you must have some kind of drop in energy, right? So how do you call that? Your voltmeter is something like this. So it has to be in parallel with the object that you're trying to measure the current at the voltage of. Okay, so basically what you're doing is trying to stop, okay, you're trying to stop the electron. Okay, so now the voltmeter measure voltage drop across, okay, across a device, and the voltmeter also has very, very high resistance. If you put it in the circuit, it will stop the flow of electron completely. You're introducing like an insane amount of traffic. Okay, most of the current will actually pass through the circuit itself. So the original circuit itself. So most of the current will actually just go through the object. Now, very little amount of percentage of the current will actually go through the voltmeter, and it's going to be picked up by the voltmeter so that the voltmeter can measure the voltage before and after. So the voltmeter takes only very little amount of current. So that means now in our pizza analogy, what happened is that means most people are going to deliver their pizza in this route. Only one in like a billion electron accidentally, took the other path and then it gets stopped. Now, why are we stopping the electron? We are trying to measure the energy, the voltage, the energy, the voltage, the pizza carried by the electron before and after it goes through a source, power source, or a load. Now, what does that mean? So you can think about it this way. So let's say you have an electron going in the direction of the current. So electron going in, and it's carrying, let's say it's carrying 4 volts. So the electron goes in, and then you stop it in here, and you say, hey, electron, how much are you carrying? 4 volts. And then the electron goes through this, right? And when it comes out, you stop the electron again. And you're asking the electron, hey, electron, how much are you carrying right now? And the electron said, 1 volt. You check the backpack. It's only carrying 1 volt right now. So what does that mean? What does that tell you about how many pizza or how much is the voltage drop across this resistor? So the voltmeter will give you a reading, which we call voltage drop, across that resistor of 3 volt. Does that make sense? Okay, so you cannot go into that person's house because you're not a police, you're not allowed to. But if I want to find out how many pizza was consumed in that house, this is something I can do, right? I will stop the pizza delivery guy before he entered the house. I will check the number of pizza that they are carrying. And then I will stop the pizza delivery guy once he exits the house. And I'll check the number of pizza that he's carrying again. Now, let's say he carries 4 pizza before he enters the house, and he only carries 1 pizza after he leaves the house, then the amount of pizza drop across that resistor, that house, must be 3. That means 3 joules of energy is consumed in that resistor. Does that make sense? Okay, so you have to collect a voltmeter in this way, parallel with the item that you're trying to measure. Okay, now what happens if you collect a voltmeter links to the item that you're trying to measure? Then the voltmeter will eat all the pizza. No one gets anything else. Remember, the voltmeter has an insanely high resistance. How high? Voltmeter usually carry millions of ohms. That means it will be the biggest customer. It will be the hungriest customer. It will actually just eat whatever the battery can produce and leave nothing for anyone. Okay? So do not collect a voltmeter in series. It will actually just shut off the circuits completely because the voltmeter is consuming all the energy, generating heat. Nothing else in the rest of the circuit will light up. Now, last item, so voltmeter, ammeter. So to measure current, okay, so what if I want to measure the amount of people going in, not the number of pizza they consume, but how many pizza delivery guys actually going through every second? Well, that's measuring current. So we need a ammeter. Ammeter is collected in series with the item that you're trying to measure. Now, what does that mean? That means you have to let the electron go through both. This is because an ammeter measures the current through. Okay, measure the current through a circuit, and it has very low resistance, so it's okay to put it in there. Now, what is the ammeter trying to count? The ammeter is actually trying to count the amount of electrons in coulombs going through the conductor wire per second. So you have to stand in the path in order to count something, right? If you create a new path like the voltmeter, then some people will take the original path, some people will take this new path that you introduced, then you're not measuring how many people go through you accurately because you provided a separate pathway. You have to be in the pathway to count the number of people going through you. You know, sometimes when you go to a shop, they have people go to a shopping mall, for example, they have people from near the door that counts how many people go in. They have like a little counter in their hand. Yeah, you have to be right next to the door. You have to be in the door. You cannot just open a new door because then other customer go through the other door. So in order to measure, so for example, so let's say you want to measure the current going through the light bulb. What do? You have to break the circuit, okay? And you have to install your ammeter this way so that your ammeter is part of the path. So no one can go into the light bulb without you knowing. Now you can actually put that before or after. So let's say this ammeter here. It's okay to put it here. Now, because which way does the electron actually go? If you're talking about electron, it actually goes this way, right? But if you're talking about current, then the current goes this way. So the current goes like this way. So technically, if you're trying to measure current going into that light bulb, right? Going into that light bulb. So if you're trying to measure the current, you can measure it at any point. It will be the same value, right? Some people ask, why is it the same value no matter where you measure in this circuit? Think about it this way. You might say, oh, Mr. Chang, doesn't the current drop when you go through the light bulb? It doesn't. The current doesn't drop. The voltage drop. Remember who are the currents? The currents are the people who deliver your food. The voltage is the food. You eat the food. You eat the voltage. You don't eat the people. Right? In most countries, that's cannibalism and it's illegal. Maybe in all countries, I'm not sure. Right? So current doesn't drop. So for example, if Pizza Hut send out 2 people delivering pizza, how many people do you expect to come back to Pizza Hut after they finish? 2. Right? Not 3. I mean, suddenly you have like more people going out. That's scary. I only hired 2 people. If I send out 2 people, and there's only one path, I expect 2 people to go through the house. I expect 2 people to leave the house. I expect 2 people to come back to the shop, right? So the current, you can measure at any location that you want if there are only one path, okay? You're just counting the number of electron going through the circuit. So for example, in this case, it would be like, like a wire like this. And how do you measure current? Well, you have to break the wire. You have to literally break it like this, and then you install your ammeter here, and the ammeter is a counter basically. Okay, so the ammeter is a counter. So it's just like, let me count. You have to be in it to count. So, and then you have, so electron going here, electron going here. So you have like 2 electron per second going through. So you should have 2 electron per second coming out, right, at the end. So then the ammeter is going to give you a reading and says, well, the current going through this point of the circuit is 2 M, right? Okay. So voltmeter. Now ammeter has very little resistance, very, very low resistance. That's why it's okay to collect them this way. That means the ammeter doesn't eat. The voltmeter eats a lot. Okay. So ammeter is like, it's like my son who doesn't like to eat too much, and voltmeter is like me who like to eat a lot. So if you put a voltmeter in series like this, it's going to stop everything because it's going to consume all the food. But ammeter is okay, and its job is to count the amount of electron going through it, so it does need to stay in the path. Okay, so this week's lessons is super long. So I will put everything in the detail, the description of the post, and have a nice week. Goodbye. Stay safe, right? That's most important. Stay safe.